Oxygen isotopes are one of the most important and valuable tools we use in reconstructing paleoclimates and past environments. Today we look at why the oxygen isotope signal exists and how we interpret this signal climatically. Here I have a simple cross-sectional diagram illustrating some of the components of the Earth system. Specifically, you see a representation of various spheres of the Earth. Portions of the hydrosphere, comprising the oceans, the atmosphere, the cryosphere, areas of frozen water, the land surface, portions of the geosphere and lithosphere, and the biosphere. And oxygen is present in each of these components or reservoirs. Today we are going to focus on oxygen in the air, oceans, and ice sheets. Oxygen, of course, is present as a gas in the atmosphere. Take a deep breath, and that air is comprised of approximately 20 to 21% oxygen. Oxygen is the second most abundant gas in the atmosphere. Oxygen is also present as water vapor in the atmosphere. Oxygen is a component of water molecules in the oceans, and it exists as frozen water in ice sheets. And we know all of these reservoirs interact with each other, and thus oxygen can be exchanged, or what we call transferred, between these reservoirs. So let's take a quick moment and briefly review the anatomy of an oxygen atom. And I'm going to draw that for you up here. All oxygen atoms have 8 protons in their nucleus, but they can have varying amounts of neutrons in their nucleus. The vast majority of oxygen atoms have 8 protons and 8 neutrons in their nucleus, which give most oxygen atoms an atomic mass of 16. O16 accounts for almost 99.8% of all the oxygen atoms that comprise the Earth's system. A small percentage of oxygen exists with 8 protons and 10 neutrons in their nucleus, and these guys have an atomic mass of 18. O18. Now, variations of the same atom, right? Atoms of the same element that have varying numbers of neutrons, like the oxygen that I've drawn here for you, are called isotopes. The oxygen atom occurs in nature mainly as these two isotopes, O16 and O18, and they're often referred to as the light and heavy oxygen isotope respectively. So we have a fixed amount of oxygen in the world, and this includes a fixed amount of the heavy and the light oxygen isotope. And these isotopes exist in differing amounts in these various reservoirs. One way we quantify these amounts is by looking at the relative abundance of heavy to light oxygen isotopes in each reservoir. So there's a different heavy to light oxygen isotope ratio in the air. There is a heavy to light oxygen isotope ratio in our oceans, and there is a heavy to light isotope ratio in our ice sheets. Scientists refer to the relative amounts of these two isotopes in a given reservoir as variations in del O18. Now, the movement or transfer of oxygen isotopes through the Earth system is a process dependent on mass and temperature. And this is where things get really interesting. When ocean water evaporates, right, this is my evaporating ocean water, water with the lighter oxygen isotope evaporates slightly more readily than water with the heavier one. And this is because O16 is about 12.5% lighter than O18, and it has a higher vibrational energy. Now, some of the O18 water also evaporates. It's just more of the O16 does. This process of favoring the transfer of one isotope of an element over another is called fractionation. And when this happens, it changes the oxygen isotope ratio of the atmosphere, and it changes the oxygen isotope ratio of the ocean, because more O16 is being evaporated into the atmosphere and more O18 is being left behind. So let's think about this. The oxygen isotope ratio of my air mass is becoming slightly more negative as we are adding a larger value to our denominator. And conversely, the oxygen isotope ratio of our oceans is becoming slightly more positive as we are adding a larger value to our numerator. As the general circulation patterns of the atmosphere move air masses to higher latitudes, these air masses cool, and water condenses where it is released as precipitation, right? Either rain or snow. And any heavier oxygen will rain out first. And this will add more O18 to our ocean, and it will further enrich our atmosphere with O16. This process of condensation and precipitation progressively fractionates the oxygen isotopes, and it further enriches our oceans in the heavier isotope and enriches our atmosphere with the lighter isotope. By the time air masses are over polar regions and snow is precipitated out to form ice sheets, this snow can be very depleted in O18 and very enriched in O16. So how do we get a climate signal from these changes? Well, during ice ages, the increased size of an ice sheet comes from precipitation containing higher amounts of the lighter isotope. So the larger the ice sheet, the more O16 is locked up in the ice, and the more O18 is left behind in our oceans. Relatively more O18 in our oceans means relatively more O18 incorporated in the calcium carbonate shells of marine organisms. This is the oxygen in the calcium carbonate shell. When these organisms die, their shells eventually fall to the bottom of the seafloor and accumulate as a permanent record of past seawater oxygen isotope ratios. And greater O18 in a marine mineral results when there is greater glaciation. And the opposite occurs during an interglacial event when ice melts. For example, if all the ice present on Antarctica and Greenland today melted and it flowed back into the oceans, it would deliver a large volume of O16-rich meltwater that would shift the ocean's average oxygen isotope ratios in a negative direction. This change in ocean chemistry would be reflected in the marine shells living at that time, and potentially preserved in the Earth's sediments for hundreds of thousands of years or more.